Hi there guys, welcome to this video where we're going to take a look at some A-level mathematics, and in particular we're going to take a look at some differentiation, how to interpret derivatives, particularly higher order derivatives, second, third order derivatives, and we're going to take a closer look at the second derivative test. From my personal experience working one-to-one with A-level math students, it seems to me that there is a lot of confusion when it comes to derivatives, how to interpret them, what are the different ways that they can be interpreted, and also with the second derivative test, when does it apply, how does it work, and so on. So hopefully in this video I can bring some clarification to these ideas. We're going to explore these ideas a little bit more thoroughly. I think this video is going to be a little bit too late to help with the 2025 A-level maths exams, but nevertheless, going forward, any A-level maths students that find this video, it will still be useful to them for future exams. So this video is going to be entirely unscripted. I don't know exactly what I'm going to say. Nevertheless, that it was something that it's something that's been on my mind for a while now. Making some videos, clarifying some of these common misunderstandings, common errors when it comes to doing particularly A-level maths and further maths. So maybe this will be the first video in a series of videos that I will upload to this YouTube channel to help you guys to clear up some of the issues that you might be having with your A-level maths studies. If you do have any ideas about anything that you'd like to see me cover in more detail, then please drop me a message in the comments section and I'll see what I can do. Okay, so let's get on with the video then. So I'm not going to go into differentiation from first principles in this video. That's something that's for a different video. I really want to concentrate on interpreting derivatives and the second derivative test. Okay, so first of all, let's just understand what we mean by derivative and how we interpret this notion of derivatives, of dy by dx and things like this. So if we start with y equals f of x, so y is, and we're going to be sticking with generally the kinds of functions that you come across at A level. So differentiation is a very difficult thing. It's at A level, you can kind of get the idea that differentiation always applies. You can always differentiate functions, and this is not the case. In fact, you do come across a couple of functions at A level where differentiation is a bit of a problem. So for example, if you've done a modulus function, y equals the modulus of x, you may be aware that there is a point when x equals 0 where where differentiation doesn't work for this function. Works everywhere else on the function, but just not at that point. And there are much more erratic functions where there's many points, where differentiation just doesn't work for the function. We're not dealing with those. We're dealing with the nice types of functions that you typically come across at A level. So we're thinking about continuous functions, nice smooth functions, and things like that. Okay. So because I don't want to get bogged down in technicalities that are way beyond A level. If you are interested in going further into differentiation, the theory of differentiation, then maybe at some point in the future I'll make some videos on that kind of stuff, or go to university and do mathematics at undergraduate level. Okay, so we've got y equals f of x. So we can differentiate this and we can get dy by dx equals f primed x. And it's important to understand that f primed x is just a function in its own right. It's called the gradient function of f of x, right? It's called a gradient function for a reason, because it's a function. Okay, it seems a bit obvious, but often when you pay attention to the language that is used to describe some of the things in mathematics, you'll find that the words are often telling you a lot about what that thing is and its property and some of its properties. So here we've got a gradient function. it's a function in its own right, but it's called a gradient function because it can be used to describe the gradient of f of x. Sorry if I'm stating the obvious here, but it is important to just clarify these things. And then we can go on to the second derivative. Okay, if this is a function in its own right, then there's no reason why we can't differentiate this thing. Okay, so when we go to the second derivative, we get f prime prime of x. But what do we have over here? Well, we typically write d2y by dx squared. Okay, the second derivative of this function. But there's also another way that we can think about this, the second derivative of this function. It's the first derivative of this function. Because what we've done is we've differentiated this to get this, but then this is a function in its own right again. We differentiate this to get this. Okay? So yes, it's the second derivative of y with respect to x, but it's also the first derivative of dy by dx with respect to x. And generally speaking, this is how the second derivative of a function is often defined, actually. That's not very good d, is it? d2y by dx squared is defined to be the first derivative of the first derivative. Okay, so d2y by dx squared is equal to d by dx of dy by dx. Well, as you can imagine, we can go on to the third derivative, d3y by dx cubed. Okay, again, these are all just functions, all of them, and we can continue on and on and on. How is the third derivative to be viewed then? Well, it can be viewed there's no single way for it to be viewed. There's all sorts of different ways for it to be viewed. And if you're stuck with one way of viewing something, this can be very limiting for you, and it can make problem solving very difficult for you. If you've got a range of different ways of interpreting something, this can give you a lot more insight into possible ways forward when it comes to trying to find a solution to a problem. Okay, so the third derivative, d3y by dx squared, is the first derivative of the second derivative. But there's no reason why we couldn't also view this as the second derivative of the first derivative. In other words, it's d2 by dx squared of dy by dx. Okay? And it's important that we've got this flexibility in the way we possibly think about these things, because this is going to play a role, by the way, in what I'm going to say later in this video, what I expect to say later in this video. These kinds of ideas are going to come into play. Okay? By the way, if you need to, with this video, be prepared to take notes. Be prepared to pause the video. Be prepared to rewatch certain bits of the video. Don't expect that just watching this, having it on in the background or something like that, is going to make any difference. Okay? There's going to be a lot of information that I'm going to be kind of unloading in this video, and that means that you probably will have to take notes, because I'm going to be rubbing things off the board as well. Sometimes some important things, but still referring back to them. So it might help if you've got a pen and paper to hand to take some notes. Okay, so because these are all functions in their own right, we can consider the graph of y equals f of x. And remember, differentiation, it's a very geometric, visual kind of thing in many ways, right? We're talking about gradients here. Gradients don't really make sense without a kind of geometric interpretation. They can be completely abstracted and just treated in a purely algebraic way. But the notion of gradient wouldn't exist without our kind of geometric interpretation of functions and things like this. So we can draw the graph of y equals f of x. We can also draw the graph of dy by dx equals f prime x. we can draw the graph of d2y by dx squared equals f prime primed x. Okay, and it's going to be important for us to acknowledge that we can draw the graphs of these things, but also that we start to understand the relationships between these graphs. Not only is there an algebraic relationship between all of these things, this is the second derivative of this is the first derivative of this, and so on, but the graph of this has some relationship to the graph of this. And it might not be terribly obvious at first glance what that relationship is, but if you kind of follow the logic through and maybe couple those graphs up with algebraic expressions and how you understand them in an algebraic sense, then things become much clearer. So let's have a look at what I mean. So let's just stick with y equals f of x, dy by dx equals f prime of x, and maybe let's think about a particular function. So let's take something like y equals x times x minus 1 times x plus 1. Okay, so it's a nice cubic. And if I were to expand this out, because I'm going to be differentiating this soon, it's going to be easier for me to differentiate when it's expanded out. So it's going to be x cubed, so minus, this is going to be x squared minus 1, so it's going to be x cubed minus x. Okay. So what does the graph of this look like? X, y. The graph has roots at minus 1, 0, and 1. It's a positive cubic, so it's going to generally look like that. Okay? But now if I differentiate this, and I'm going to clear a bit more space. If I differentiate, now I've got dy by dx, this is going to be equal to 3x squared minus 1. Okay, what does the graph of this look like? 3x squared minus 1. So we've got x here, and we don't have y here, we've got dy by dx. Okay, so 3x squared minus 1 is just going to look, it's a positive quadratic, it's going to look something like that. Minus 1, that's 0. We don't actually care too much what the roots are, but just for sake of argument, they're going to be at what? I better solve this, hadn't I? X squared equals a third. Okay, so 1 over root 3 and minus 1 over square root of 3. Or root 3 over 3, whichever you prefer. It doesn't really make any difference. Okay, so this is a very simple case, but it's surprising to me how unfamiliar people are at A-level maths with the idea that I'm about to kind of demonstrate. To me, it's very straightforward, but obviously I've got an advantage that I've got a lot of experience with differentiation and mathematics and things like that. But this is an essential idea, in my opinion. This is critical, really, to starting to develop a good, thorough understanding of differentiation and really starting to see differentiation arguably for what it is. Okay, so what I see then is, let's say I start here on my graph of y equals x cubed minus x, or f of x. What do I see? If I were to draw a tangent line here, what would I see? I'd see a very positive tangent, a positive gradient tangent line. So the gradient is positive here, so I would expect the gradient function to be above the x-axis. And if it's very positive, if the gradient of the tangent is very positive, I would expect this point to be quite a distance above the x-axis. But what happens then? The gradient, as I move towards this point here, minus 1, as I move towards this turning point here, what happens? The gradient's still positive, but it's decreasing. Well, that's what I see here, positive. The graph is positive. I'm not talking about the gradients of the graph of this graph. I'm talking about the gradients here, but the points over here. gradients on this graph correspond to points on this graph. So the gradient is positive but decreasing. The points are moving further and further down towards the x-axis. They're decreasing in value there. The y-coordinates are decreasing in value. And then what happens? I get to this point here. And what's the gradient at that point? 0. Well, that must be this point then, at minus 1 over the square root of 3. Because this is the measure of the gradient. Right? The y-coordinates of these points are telling me what the gradient is at the corresponding points over here, right? So if I choose x equals a here, and I draw a tangent line in here, I'm not going to do it because it'll mess up it'll make the graph look a bit cluttered, and draw the gradient, the tangent line in at that point, and then I come over here, what I will find x equals a over here, the y-coordinate of this point is the gradient of the tangent line at this point. And this is very, very important to understand. Okay, so we've got to this point now. The gradient here is 0. The y-coordinate of this point is 0. But then what happens? The gradient becomes negative. It starts out slightly negative, but it gets a bit more negative. That's what we see. Slightly negative, a bit more negative. Until we get to this point where the gradient is as negative as it's going to get. And then it's still negative, but it's decreasing. So that's where we get this point of inflection here, right? And that's this point here. The gradient now is maximally negative, and now it's starting to increase again. And we get to this point here, this minimum point. Again, the gradient is equal to 0, and that corresponds to this point here, where the graph of the gradient function passes through the x-axis. The y-coordinate is therefore 0. And then the gradient becomes positive, and increasingly so. That's what we see. Positive and increasingly so. So you can follow the behavior of the tangent, the gradient of the tangent on here, through to the points on here. And if you make that connection, you're starting to make some real progress with differentiation. If you can't make that connection, differentiation is always going to be something that, in my opinion, you're going to struggle with. Okay, so why is this important? Because once you get this, you can start to see how the second derivative test kind of works. Okay, so let's have a look at the second derivative test. By the way, if there is anything, because I'm doing this unscripted, if there is anything that you find that I don't explain particularly clearly and that you want further clarification on, just leave a message just leave a comment in the comments section. Ask the question, I'll be happy to help you. So let's have a look at the second derivative test. What does the second derivative test say? So we've got y equals f of x. Now suppose that dy by dx equals 0 at some point x equals a. And then suppose also that at x equals a, d2y by dx squared is greater than 0. Well, this will mean that we've got x equals a is a, and we've got to be careful here. So d2y by dx squared is greater than 0. X equals a is a minimum point. Corresponds to a minimum point. And this is what we're going to get some clarification on, but it's not the only thing that I want to clarify in this video. Now, there's three possibilities for the value of d2y by dx squared. Either d2y by dx squared is greater than 0, it's less than 0, or d2y by dx squared is equal to 0. Okay, so if we've got greater than 0, x equals a is a minimum point, less than 0, x equals a is a maximum point, And of course, we've got three types of turning point. Okay, we've got maximum point, we've got minimum point, and we've got point of inflection. So we've got the maximum point accounted for, we've got the minimum point accounted for. So surely this corresponds to point of inflection, right? It doesn't. Okay, the second derivative test is inconclusive in this particular case. Okay, now there's some important points that I need to make regarding this second derivative test. One, the second derivative test applies at points that we know to be turning points. Okay, so notice before I even started to talk about second derivative values of second derivatives, I said suppose that dy by dx is equal to 0 at x equals a. I'm establishing that this point is actually a turning point. We understand when we say turning points, we understand those as being the points on the graph of our function where the gradient is equal to 0. In other words, dy by dx is equal to 0. Okay? And again, we are just dealing with nice functions. If you go into university level maths, you'll see this, you'll hear this all the time. Suppose that this function is sufficiently nice. I'll suppose that the solution to this differential equation is sufficiently nice and things like this. What it means is just, we don't really want to get bogged down with really technical details at this stage. So we're just going to assume that what we're dealing with has all the kinds of properties that we want it to have in order for this to work. So this is good to get a basic understanding of an idea. Now, of course, at some point, those technical details do have to be dealt with. Okay, so we might, just to get a handle on an idea, we might deal with sufficiently nice functions, which is what we're doing here. But further down the line, we have to acknowledge the fact that not all functions are sufficiently nice. There are some sufficiently horrible functions that we've got to take into consideration and we've got to deal with them. But just for the time being, just to get a handle on this idea, then we're just gonna take things nice and steady. Okay, so anybody out there that's kind of screaming at the computer screen saying, no, what about this? What about that? What about the other? I'm fully aware of these things. It's just I'm choosing to ignore them right now because it's not the main focus of this video. Okay, so another point that we need that I need to make is that the second derivative test doesn't always tell us what the type of a turning point is. Okay, the second derivative test doesn't always work. Even when it applies, it doesn't always work, in the sense that it can come back inconclusive. Now, if it's either of these cases, this is conclusive, right? There's no grey area here. So it's not that, well, it's sometimes a minimum point when the second derivative is greater than 0. It's sometimes a maximum. No, it's if the second derivative is greater than 0, x equals a is a minimum point. That's it. End of story. Similarly, d2y by dx squared is less than 0. X equals a is a maximum point. That's it. Full stop. End of. Okay, but d2y by dx squared equals 0, we get inconclusive. So what do we do then? Well, at that point, we're going to have to do a bit more analysis. What that will often involve is going on to the third derivative, okay, and seeing what happens with the third derivative, okay? But do not, under any circumstances, conclude under these conditions, when you've got the second derivative is equal to 0, that this must be a point of inflection. It's not forced to be. It might hint at the possibility of a point of inflection, but it's not forced to be. And we can see this, for example, if we take y equals x to the power of 4. If we take y equals x to the power of 4, the first derivative of this, dy by dx, is 4x cubed. The second derivative, d2y by dx squared, is 12x squared. Okay, so this has a turning point when x is equal to 0. X equals 0 is a turning point, and the value of the second derivative at x equals 0 is 0. Okay, but what type of a turning point do we have here? Well, even if we just go by the graph of y equals x to the power of 4, we can see that it's a minimum point, right? Now, okay, generally speaking, we can't make definitive conclusions based on what we see in a graph, but it's not difficult to kind of see that it's got to be a minimum point and it can't be a point of inflection or something else. Although a more careful analysis, algebraic analysis, would reveal that yes, we do have a minimum point at y equals x to the power of 4, x equals 0. Okay, so in other words, we're getting that the second derivative is equal to 0, but we've actually got a minimum point here. And if we choose something like y equals minus x to the power of 4, we'll get exactly the same thing, right? The first derivative and the second derivative, both at x equals 0, will be 0. And yet here we've got a maximum point. So the second derivative equals 0 could correspond to a minimum point, maximum point, or points of inflection. Let's take y equals x to the power of 5, for example. It's got points of inflection at x equals 0, but the first and second derivative at x equals 0 will be 0. So in other words, the second derivative equal to 0 at a point that we know to be a turning point is inconclusive. Okay, so let's just have a little bit of a look about why these two work in the way that they do, because this is going to be important when we come on to look at the third derivative to try to figure out. We can often figure out what type of a turning point we've got. If we find that the second derivative test is inconclusive, going to the third derivative can sometimes reveal to us what kind of a turning point we've got. But I'll say more about that later in the video. So let's just get rid of that for now, and let's just concentrate on this first case. So we've got the dy by dx equals 0 at x equals a, and the second derivative at x equals a is greater than 0. Well, actually, this is what we want to show, why this is the case. So let's start with y equals f of x, and what we've got, minimum point. Okay, so here's our minimum point, or our graph around our minimum point. Now understand that this is potentially very zoomed in on our function here. We're not taking a kind of global perspective of our function. We're zooming in as far as we need to for this idea to work. Again, everything's nice here. We're not dealing with pathological cases. We're dealing with nice cases. So typically around a minimum point, this is the kind of thing that we're going to see, even if we've got to zoom right in on the function. Okay, so x, d2y by dx, dy by dx even. And let's have a look. Okay, so what we can see is that if we draw a tangent, like if we go to the left of a little bit, so a little bit less, the x-coordinate is less than a, we can see that the gradient is negative. The gradient of the tangent line is going to be negative, and it's going to be, let's say, so this is x equals a. It's going to be down here somewhere, maybe. Remember, gradients of tangent lines here correspond to points over here, right? So as we move closer to a, what happens to the gradient of the tangent line? It's still negative, but it gets less so, less negative. Okay, so that's what we see here. We get less and less negative as we move towards a. And then when we get to a, the gradient of the tangent line is going to be 0. And then once we get beyond a, what we find is that the gradient starts off slightly positive and then it becomes increasingly so. So we get something that looks maybe like this. Okay, so what does the graph of dy by dx look like? Well, it might, not forced to, it might look something like this. Okay, it might look something like that. And I've drawn it deliberately so that it doesn't have, that dy by dx doesn't have a point of inflection at A, okay? It's got a definite non-zero gradient. Okay, but remember, the second derivative is the derivative of the first derivative. So now we start considering the gradient of points on this graph. We can correspond those gradients of tangent lines with points on another graph, which is the derivative of this, or the second derivative of this, whichever we prefer. So what does that look like? X, we've got d2y by dx squared now. So what does the gradient of this look like? Well, it's positive. It looks positive. And even at x equals a, the gradient of the tangent line here is still positive, so it's going to be up here somewhere, depending on how positive the gradient is. So in other words, when we've got a minimum point, we've got that dy by dx is equal to 0 at x equals a, but because in this particular case, the gradient of the tangent line of the gradient function at x equals a is positive, we get this. Okay, we get a point here. In other words, d2y by dx squared is greater than 0. Similarly, if we had things the other way around, so if we had a maximum, we get a graph dy by dx that kind of goes this way, but we'd have a negative gradient. Again, I'm deliberately choosing the gradient function so that it's got a non-zero gradient. So if the graph starts up here and finishes down here, then it has a negative gradient as you go through A, and therefore we'll get a point that's down here, below the x-axis, on the graph of the second derivative, which corresponds to d2y by dx squared is less than 0 when we've got a maximum point. Okay, but we've already seen that d2y by dx squared equals 0 could correspond to maximum point, minimum point, or point of inflection, and in fact is inconclusive. So let's have a look, what further can we do in that case to try to establish what kind of a turning point we might have? The answer is that we can try going on to the third derivative, which may itself be inconclusive. Let's see. Suppose also at x equals a that d2y by dx squared is equal to 0. So now suppose that d3y by dx squared is not equal to 0 at x equals a. That implies x equals a is a point of inflection. Okay, on the other hand, if we've got d3y by dx cubed, is equal to 0 at x equals a, that implies, again, inconclusive. So we're getting a lot of potentially inconclusive results here. Okay, so let's have a look then at why this works. Okay, why can we conclude, if we've gone to the third derivative and that is non-zero, why can we conclude that we've got a point of inflection? Okay. Right, so one way that we can understand why this works now is if potentially we think about the third derivative as the second derivative of the first derivative. So now we can view things as a kind of second derivative test on the first derivative. Okay, I'll show you what I mean. So, x dy by dx x d2y by dx squared, and now we've got the third derivative. x d3y by dx cubed. Okay, so there's two possibilities here. If the third derivative is not equal to 0, then either the third derivative is greater than 0 or it's less than 0. So let's consider the case where the third derivative is greater than 0 at x equals a. So greater than 0. So what does that mean on the second derivative? Well, we've just kind of seen, right? That means that we've got at x equals a, we've got a positive gradient, right? We know that the value of the second derivative at x equals a is 0, but we've got a positive gradient there, right? So our function, our second derivative is potentially going to look something like this. I'm not saying that it will look exactly like that, it's just this is representative of the kind of thing that we might see. But we also know that that corresponds to a minimum over here, right? Remember, we're thinking about this as a second derivative test on the first derivative. So we've got a minimum point at x equals a. Okay, so what does that, so we're kind of working backwards here. We've gone from the third derivative. What does that tell us about the second derivative? What does that tell us about the first derivative? What does that tell us now about the original function? Because remember, the values, the y coordinates of the points on here corresponds to the gradients of the tangent lines at the corresponding points over on the original function. So I'm not going to draw it in, but you can see here that the gradient of, the value of dy by dx is positive here, but decreasing. Okay, positive but decreasing. So, okay, I will draw it. I'm gonna rub this off over here, just so that I've got a bit of space. So now we've got the graph of y against x, and just to avoid any confusion, I'll get rid of that as well. So now we're thinking, how does the behaviour of this determine what the graph of y looks like? So we've got positive gradient, but decreasingly positive. Well, that's going to look something like that. And then we get a gradient of 0. But then what happens? The gradient goes positive again. So the gradient's positive, decreasingly so, right down to 0, and then starts to become positive again and increasingly so. So I get something like that, a point of inflection. Similarly, if I'd started with d3y by dx cubed below the x-axis, in other words, if d3y by dx squared, dx cubed is less than 0, that would correspond on the second derivative to a negative gradient, which would correspond to a maximum point here, which would correspond to a point of inflection, but in the opposite kind of direction. So how these tests work can be best understood with reference to the various graphs that are involved and the relationships between those graphs. If you're ignorant of those relationships, if you're ignorant of the fact that you can actually even draw the graphs of these things, then it makes all of this just very difficult to remember, because it seems like a web and a tangle of all different conditions. Okay, and that's not a good way to. It's not a good way to try to remember information as just kind of a list of miscellaneous items, like a shopping list. It's best understood through logic and understanding. Mathematics is a logical subject. To do mathematics effectively, you have to understand, and by that I don't just mean be able to carry out a set process. I mean actually understand why the process works. Okay, so that's how the third derivative comes into play. Of course, we could have d3y by dx cubed is equal to 0, in which case we get inconclusive. What do we do then? On to the fourth derivative. Okay, So understand that there's a whole series of derivative tests that we can potentially use. If the second derivative test doesn't work, and we go to the third derivative and that doesn't tell us anything either, then we go to the fourth derivative and we basically do a fourth derivative test, which works in the same way as the second derivative test, but just with fourth derivatives. If that comes back inconclusive, we go to the fifth derivative. And if that's not equal to 0, then we've got a point of inflection. So odd number derivatives are good for telling us when we've got points of inflection. Even numbers are good for telling us when we've got maximum points and minimum points. Okay, but there's a sixth derivative test, an eighth derivative test, a 10th derivative test. We can go as far as we need to, and it really depends on the nature of the function. Obviously, in practice, we're kind of limited as to how far we're willing to go with this. But in theory, from a purely mathematical perspective, you can go to any test that that's appropriate. No matter how far down, you can go to the 1 trillionth derivative test if you really need to, and if that shows you that you've got maximum point, then so be it. Okay. So there's various different combinations that you've got to take into consideration. Also, by the way, notice that this is all centered around a particular case as well. Here, dy by dx equals 0 at x equals a. If dy by dx is not equal to 0 at x equals a, and you get that the second derivative is equal to 0 at x equals a, then you can conclude that you've got a point of inflection. Okay? So again, it's down to these odd numbered derivatives being the derivatives that really determine when we've got points of inflection. But when you've got a turning point involved, the second derivative test is inconclusive when second derivative is equal to 0. But just for clarity, I'll say it one more time. If we know, for example, that, in fact, I'll write it on the board. If we know that dy by dx is not equal to 0 at x equals 0, suppose also that at x equals a, d2y by dx squared is equal to 0. That means, again, you've got a point of inflection. But this is not going to be a point of inflection that's parallel to the x-axis. In this case, you're going to get a point of inflection that's going to be oblique. It's going to be on a slant. Okay, so think about the graph that I drew earlier, the x cubed minus x, that's got a point of inflection at x equals 0. It doesn't have a turning point there, but you calculate the value of the second derivative there, it's going to be 0. Okay, so your point of inflection might look something like, if I can draw it, might look something like that. Okay, so the gradient here is positive, very positive, decreasingly so, but it doesn't decrease all the way down to 0. It decreases to a minimum value, minimum positive value, and then it starts to increase again. So you can get points of inflection that are not parallel to the x-axis, and that's what you've got in this case. In fact, the gradient, if this is x equals a, then the minimum value that you obtain is going to be the value of dy by dx at x equals a. Okay. Okay, so that looks at derivative tests and how to interpret derivatives and things like that. Is there a case, because I've suggested that you can go as far as you want with these derivatives. You can go to the fourth derivative, sixth derivative, trillionth derivative test if you really need to. What if none of these work? Is that even possible? Is it possible for you to just keep going through these derivative tests and find that none of them are conclusive? And we're not talking about being limited by time here, being limited by the physical world that we live in and the physical limitations that we're subject to. We're talking even in a mathematical sense where you can go off to infinity and things like that. And the answer to that is yes, that there are cases where no derivative test is going to work to tell you what kind of a turning point you've got with your function. I'll give you an example of a function. It's a well-worn function amongst undergraduate students. So if we've got f of x is equal to e to the power of minus 1 over x squared for x is not equal to 0 and 0 for x is equal to 0. The graph of this, by the way, is not a particularly difficult graph to draw. You can draw it on Desmos or some graphing software if you want to, but the graph looks roughly like this. So it's got a horizontal asymptote at 1, at y equals 1. And the graph looks roughly like this. Okay, so it's not a terribly complicated graph. It's a bit wobbly by the looks of it on my camera. But this has a minimum point at x equals 0. It's differentiable. I'm not going to go through all of the fine details and the proof of all of this. Take my word for it for the time being. It's differentiable. It's continuous at x equals 0. It's differentiable. In fact, it's infinitely differentiable at x equals 0. All its derivatives exist, and all of the derivatives are equal to 0 at this point, at x equals 0. So in other words, but you can see we've got a minimum point there. So what does this mean? It means that it doesn't matter which derivative test you try to apply to this, it's never going to tell you that you've got a minimum point here. So how would you determine that you've got a minimum point here? You'd have to use some other techniques. Okay, there are other techniques that you can potentially use to tell you when you've got maximum points, minimum points, and things like this. But unfortunately, so the second derivative test, the derivative tests are not the only way that mathematicians have of determining whether you've got a maximum point or a minimum point and things like this. So there's other techniques that you'd need to use, but that's a good case, a good situation where the derivative tests just don't work. Okay, no matter how hard you try. Now, of course, at A level, you're not going to be presented with a function such as this, unless, I mean, there is the possibility on maybe a step paper, or if you're doing the mathematics admissions test, that you could come across some quite unusual functions from time to time with quite unusual properties that maybe you're not used to, but in that case, you will typically be given a bit of guidance in relation to these functions. I'm not sure that they would go so far as to give you something like this, but you never know. But there are such functions out there. And if you go on to undergraduate level maths at university, you'll come across all this kind of stuff. And it will just become normal for you to think about functions as being differentiable or not differentiable. Rather than at A level, you kind of get the idea that all functions are just differentiable and you can always differentiate functions. This is really not the case. So I hope that in this video, I've brought some sort of clarification to how derivative tests work. If there is anything that you're still not clear about, then please let me know further down the line. If I need to remake this video, then I can do. But also, if there's anything else with A-level maths that you would like some more information on, if you're having particular difficulties with it, let me know. By the way, I don't make any money from these videos that I make. I make these videos because I want to make them, because I enjoy making them, and because I enjoy helping you to reach your potential. So if you do like these videos and you want me to continue making them, please show your support for this channel by hitting the subscribe button and hitting the like button. So that's about it for this video. So I say thank you for watching, and I'll see you in the next video. Cheers, guys.